Greetings everyone. Welcome to the first example for the UAV FSO channel link modeling. In this particular example, we'll cover the default parameters for the UAV component, and we'll also examine the effect of beam wandering and mechanical jitter on the power budget and the final beam. In this particular example, we have a UAV that is hovering around 500 meters above the ground level. So this is the receiver altitude, and the transmitter is a base station that's fixed with 50 meters above the ground. The line of sight distance between transmitter and receiver is 6 kilometers, and this indicates the range for our component. This particular figure is not to scale, and this configuration corresponds to the default settings in the UAV channel. So the UAV channel models the propagation of light from the transmitter to the receiver. We'll also examine how it affects the spatial mode propagation and the also power budget. In this simple example, we have a CW laser that is fed into the component. There is no incoming mode. As such, a spatial mode is generated inside the component. To give an idea of what the Gaussian beam will look like, you can check the beam waist, which is one of the primary inputs, which is 50 millimeters. In order for the component to operate properly, you must ensure that the component has the appropriate numerical window size that enables adequate modeling of the beam propagation after transmission. So let's check here, for example, if we click on the settings of the component, you can see there's a variety of tabs, the main tab, the weather and scintillation, and in the beam XY profile tab, you see here that there is a numerical window space with X, space with Y. XY here do not refer to the polarizations, but refer to the dimensions of the numerical window where which the spatial mode is displayed. And these are scripted from the main layout global variables. As such, for a 50 millimeter beam waist, you would like to ensure that you have adequate spatial window width X and width Y. And in this particular example, we have 100 1000 millimeters for X and 1000 millimeters for Y, and the grid spacing for X and Y is 1 millimeter each. Inside the component, you can see here that we select UAV role, and in this configuration, the TX is a fixed base station to the ground, and the RX is the UAV, so we select the first mode here. This is particularly important when it comes to estimating the mechanical jitter, or the jitter of the receiver UAV, and how it affects the wander or the displacement of the spatial beam. We have a range of 6 kilometers. You have the attenuation. You can set it yourself, or you can use the FSO weather conditions to estimate what the attenuation per kilometer is. We also have a few variables here: geometric loss, free space path, and geometric gain. These two are tied together and they're coupled, the free space path loss and geometric gain. You have to bear in mind that the validity of the equations used to approximate those two depend on the transmission distance. If the transmission distance is small or short, these equations are no longer valid, and the approximation only works for far field. The term for geometric loss also depends on the transmitter diameter aperture and the receiver aperture diameter, and the divergence angle and the distance r. Under certain conditions, the geometric loss can actually translate into gain, and this component will just cap that at 0 dB or unity. So in this particular sense, we have 50 millimeter beam waist at the transmitter side. We have a transmitter height of 50 meters as indicated in the diagram, and the receiver or the UAV is 500 meters altitude. There's also discretization steps in both altitude and in range, and these actually are critical for the numerical integration of the CN squared, or the index of refractive structure. This is relevant for the calculations of beam wandering and also for the calculation of the spatial effects in the second example. So if we let's assess the performance of this particular default settings right now and have a look at the output result. So after simulation is computed, you can look at your output beam, and you can see here in the results right away that the transmitter beam waist is 50 millimeters and the receiver beam waist is 77 millimeters. And this is also indicated in the spatial output mode here as well. So this is the 100 millimeter range here. So the 77 millimeters is your new after transmission beam waist. If you check the component and you check the 2D plots here, you can actually see the beam evolution along the propagation distance, and it goes from 50 millimeters to 77 millimeters. This is the standard Gaussian enhancement of the beam waist in the free space optics calculations. And if you observe also in the settings, you have observed the receiver aperture. So this is the aperture of the receiver capture area, and you can also see the received beam spot size. And as you can see that the beam is fully enclosed inside the received aperture, and as such you should have zero loss due to this mismatch in overlap, and this is indicated in the result here for the receiver total aperture capture loss, 0 dB. We'll also now examine the effect of the mechanical vibrations on the UAV in the receiver end. If we set, for example, here this to beam jitter in the field shift is on. And you have to note of this message here. This is a message that indicates to you that in this configuration, the TX is actually a base station that's fixed to the ground. As such, the TX jitter is not counted. And the effective jitter will come out from the RX and the angular tilt as well. So if we run this particular example, and we have to see the variations here, and you notice here in the results section that there is beam jitter RMS displacement, and then you have the actual applied displacement X and Y and the total displacements. And the total displacement is here because we have also beam wandering displacement that could be superimposed on the mechanical jitter displacement. If you observe here in the mode, you can see there's a slight shift in the mode location, and this will become more apparent if we look at the internal view here, and we just look at the 2D view. The blue is the center of the receiver aperture, and the red is the effect of the mechanical beam wandering, very slight jitter. And there's a very slight loss here because the Gaussian beam has tails that evanescent outside, and you're not capturing the maxima of the Gaussian beam in this configuration. If we attempt to add additional effects, we add the beam wandering effect, and this could be added over the entire link from TX to RX, or indeed over the turbulence region only. This is another option. Since we're not having turbulence in this modeling, we'll consider the entire link. What you will notice is that the beam wandering will force in the scintillation tab that the Fried parameter will be calculated from the index refractive structure, CN, and the CN model is fixed at the altitude model. For the beam wandering, a altitude-dependent CN square is absolutely necessary, and in this case, the HVP. The user can certainly select a few other variations, but for this particular run, we'll go with HVP. The mathematics behind the beam wandering effect is detailed in the component help, and you'll realize that an integration of the CN square is needed over a particular altitude range, hence the requirement on the existence of an altitude model for the CN square. And the discretization of the number of steps in altitude and in range also play a critical role. If you examine here, the movement of the beam relative to the center is significant now, even more than the effect of the jitter alone. And you can actually examine this more succinctly by looking at the component. And you can see here that with the aperture circle for the aperture receiver, and this is the spot size, rough spot size of the received beam, and you can see that it's offset, and this will result in significant aperture capture loss, is indicated by 8.9 dB in this case, which contributes to the total channel loss, which can be observed from the power loss as well for the transmitted signal. And as a consequence of enabling the beam wandering, we will also be able to look at the performance of other curves involved in the altitude model. So here we have the CN square as a function of refractive index structure, function of altitude. This is a very small altitude elevation for the UAV. So the transmitter is at 50 meters and the UAV is 500 meters. You can see this is the change of the CN square. As you can see, closer to the base station, it's high. And as you get closer to the UAV, it becomes low. You can also look at how this index factor structure changes with the slanted path from 0 to 6,000 meters. You can also examine the cumulative fright parameter and the also horizontal fright parameter. The values of the fright parameter become relevant in the example number 2, where we examine the effect of spatial effects on the spatial mode and turbulence effects on the spatial mode, and how it affects the power budget and how it affects the final output from the component. Thank you for your attention.